It doesn't say what's the enthalpy change for the system.
It's saying that it's going to burn in air. So
It's saying how much has evolved. That would be an absolute value. All right. Standard enthalpy of formation data. That's the heat change that results when a mole of a compound is formed from its elements. Standard enthalpy of formation of any element in its most stable form is 0. So O2 is the most stable form of oxygen. It has an enthalpy of formation of 0. O3 is not the most stable form of oxygen. You know what O3 is, Brian Patrick Henry? Ozone. So that would require 142 kilojoules per mole to form it.
no, H2O2 is.
Graphite is the most stable form of carbon. Diamond is not. There's a table of standard enthalpies of formation. It's found in the back of your book. You're going to be using it a lot. The standard enthalpy of reaction is the enthalpy of a reaction carried out at 1 atmosphere. Did I just...
Whoa.
Okay, take a moment, read that, and just take it in. And then we're going to talk about it a little bit.
We did this last year, Hess's law.
Did I have you do some of these in pre-AP?
Hess's law.
C delta H at standard.
It looks a hot mess.
That's what Eddie told me.
It's not that complicated once you break it down, though. All right, let's start at the bottom of this slide. What's a state function?
Standard function.
If I talked about enthalpy of formation last year, I know I talked about state functions. Does anybody remember what a state function is? No? Wendy? Come on, girl. Ackerman, we need you. What's a state function? Geez, at least in my other class, someone read the definition from the PowerPoint. Well, Mr. Houston, a state function, it doesn't matter how you get there, only where you start and end. How hard was that? It's right there.
Where does it say that?
Right next to an enthalpy as a state function.
It doesn't matter how you get there, only where you start and end.
So what does that mean?
It means it's a state function.
They don't care about that.
It means it's a state function, okay.
They don't.
It doesn't matter because it's a state function.
Well, it matters where you start and finish.
They don't care about the middle steps. Just
Yeah, we don't care if the reaction occurs in 5 steps or in 1 step. The only thing that matters is where you start and where you finish as far as the energy change. Just like, let's say, here's the United States. We're here in Houston.
where's Mexico?
It looks like a whale.
Mexico's down here. So we're here in Houston, and here's Denver.
Very accurate.
We could go from Houston to Denver and go from a little bit above sea level to 5,000 feet. And our elevation change would be about 5,000 feet. Right? Or we could fly to Los Angeles, then Seattle, Boston, New York, Miami, Chicago, and then over to Denver.
Go to Mexico City.
Our elevate, why wouldn't we? That sounds like fun. It's going to be a good weekend.
Mexico City?
Huh?
Where?
Let's go to
Oh, okay. Never mind.
You want to go to Los Angeles, Seattle, Boston, New York, Miami, Chicago, and Denver?
That sounds fun.
That sounds fun, but you said Mexico City.
Mexico City's down here. We're not down here.
Yeah,
But our elevation change, even if we did all that, our elevation change would be a state function. It would still be 5,000 feet. We went from Houston, we ended up in Denver. Doesn't matter if it took 6 steps or 1 step. Okay? All right, so why the heck is that relevant to enthalpy change? What do we care? Well, we've got data in the back of our book for the enthalpy change for the formation of every compound or element that you can imagine. Well,
Oh, really?
that you can imagine.
That sounds like a
With
challenge.
your limited imaginations. Okay? So if we know what it takes to form this, and what it takes to form this, then we know our starting point. And if we know what it takes to form this and form this, we know our ending point. It doesn't matter how we get there. It doesn't matter that we calculated that enthalpy of formations completely differently. We know where we start, we know where we finish. Enthalpy change is a state function. We can figure out the enthalpy change for this reaction. And all those enthalpies of formation are determined experimentally. So I'm going to give you a printout that we're going to use in the class of enthalpies of formation. It may be slightly different than you'll see on your online homework. The numbers will be close. They're all determined experimentally. So there'll be a little bit of variation. Might be slightly, what you're given on the online homework might be slightly different from what's in the back of your textbook. It's okay. Just do the calculation right. You get the answer that's close. Okay? Hess's law. When reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. State function. Okay, so let's break down this nasty looking equation here. The delta H for the reaction will be equal to the enthalpy of formation of products minus the enthalpy of formation of reactants. Okay? Whatever it is. If it's an element in its most stable form, it'd be 0. That's easy math. All right. Look at this. It's products minus reactants, right? So we have C as a product. What are we doing with the coefficient? Little c.
You put it in the front.
What am I, mathematically, what am I doing?
Multiply.
Multiplying. So I'm going to take the enthalpy of formation of whatever C is, after I look it up in the table, multiply it by the coefficient. Okay? And then we'll add that to whatever D is, and then we'll subtract the enthalpy of formation of the reactants. It looks worse than it is. But I'm going to caution you, there's lots of places to make mistakes because you're multiplying, and then you're adding, and then you're subtracting, and you've got positive values and negative values, and if you're not careful, you try to do it all at once in your calculator, you're probably going to get it wrong. Or you're going to break it down step by step.
Well, never.
Okay? Just be careful. You get in too big a hurry, you make mistakes. All right, benzene, C6H6, burns in air to produce carbon dioxide and liquid water. How much heat is released per mole of benzene combusted? The standard enthalpy of formation of benzene is 49.04 kilojoules per mole. There's our equation. It's balanced for us. Yay. Delta H for the reaction is equal to the delta H of formation of products minus delta H of formation of reactants.
Yeah.
Just right here. Okay. How we doing on time there, folks?
We're doing good. We got the second one.
This is the second one? Okay, so there's the equation, plugging in the numbers from the coefficients from the balanced equation. And if we look up all the numbers, products minus reactants, okay? You know where that 393.5 and the 285.83 came from?
In the back of the book.
Assuming it came from the table.
Table in the back of the book. Or this table that I'm going to give you here. I don't know if I have enough copies.
Really?
Really?
What?
Half the class is missing and he says I don't have enough classes.
I was running short of time.
You can't count.
And we're gonna work in groups in a little bit anyway, so it doesn't matter.
Groups.
Yes. The people in
Atomic
color
color
behind.
on a black and white topic.
Am I right?
Huh?
It said atomic colors on a black and white topic.
I wasn't really interested in that part.
Very useful.
Black.
What are atomic colors?
Okay,
Thanks.
all right, let's look at the wording of this question. It's asking for how much heat is released per mole of benzene. We calculated the delta H for the reaction. So for that reaction, what?
Why has One Direction on here?
I don't know.
What?
It's my favorite band. Actually, I like One Direction. Who did that? Someone in my sixth period did that. Who would have a sticker of One Direction? On
Yesterday,
them.
Valentine's here, Valentine's Day.
Yeah.
It was probably too
Lovely
dope.
Valentine that is.
It's probably too dope. She had One Direction cards.
Where were we? Oh, the question is asking how much heat is released per
That
mole.
on.
Per mole. So for our reaction, look at the coefficient for benzene. Our delta H for the reactant is the combustion of 2 moles. Do you see that?
Yes.
So we're going to divide by 2 to find out how much per mole. Or, if you prefer, if it's asking for 1 mole and this is 2, you can make this 1, make this 7.5, 6, and 3. Whatever works for you.
That's smarticle.
Or you can just divide by 2 at the end. Alright, I'm going to stop there. We'll practice some Hess's Law problems Monday, or Tuesday. Yes, Ryan Patrick Henry.
This is kind of way far back from the notes, but you know how you would, whenever you finish determining whatever your value would be, and it either comes up negative or positive, right?
I'm sorry?
Whenever you finish determining your value, in this case that one was negative, how do you determine whether it's endothermic or exothermic, or whether it releases or gains energy or whatever?
If it's negative, is the system gaining or losing energy? Huh?
It's losing, making it.
If it's negative, the system has lost energy. So if the system has lost energy, is it endothermic or exothermic?
Alright, I got it.
No,
That's important. We got to get that straight in our head.
I got it.
Because if we don't understand that, then we're going to get whether it's spontaneous or not wrong every time.